In this video, we are summarizing the work that we did in class regarding electrophilic aromatic substitution in substituted benzene. In particular, we were looking at the nitration, comparing benzene versus toluene versus trifluoromethyl benzene. We saw that when we're considering the rate of reaction, toluene reacts 20 times faster than benzene, but trifluoromethylbenzene reacts about 40,000 times slower. We also saw a difference in the product ratio, where toluene leads to a majority ortho followed by para and only a small amount of meta, whereas in the case of the trifluoromethylbenzene, meta is the major product, followed by a small amount of ortho and an even smaller amount of para. So we want to come to an understanding of why there is this difference in rate and why there's a difference in product ratios. Let's look first at the reaction of toluene with the electrophile that's generated from nitric acid and sulfuric acid. Now it's possible that we can think about the hinge here. These electrons will be shared with the nitrogen, and that gives us this intermediate where the nitro group is now connected to this carbon and the other carbon is left with a carbocation. We can draw additional resonance structures. We can imagine these electrons move here to give us this intermediate. Imagine these electrons move here to give us this intermediate. Now the resonance hybrid, which I didn't leave space for, is going to look like this, where we have partial double bond character all around here, but not along the bonds to the carbon with the nitro group, because remember there's also a hydrogen here. And then we have a partial plus on the positions that are ortho to the incoming nitro group and para to the incoming nitro group. And then after a proton is removed, that leads to the ortho nitro toluene. Toluene can also react. Imagine this is the hinge and the electrons open up this way, giving us this intermediate. Now we can imagine these electrons move here, resulting in this carbocation, and then these electrons move here, resulting in this carbocation. The resonance hybrid for this one, here is our methyl group and the nitro group, and we have partial double bond character around here with a partial plus at these positions. And then finally that leads to this product. The third option is that it's from the para position where the electrons move out so that the carbon becomes connected to the nitro group, resulting in the formation of this carbocation. We can imagine these electrons move over to give this carbocation. These electrons move over to give this carbocation. If we remove a proton, then that leads to the para product. But also we should think about the resonance hybrid, which is going to look something like this. So we have double bond character around here, partial double bond character, and then we have a partial plus, and partial plus. Now, if we look at the individual resonance structures, notice that here we have a tertiary carbocation, whereas in the other cases we have secondary. But more important, if we think about the nature of this substituent, the methyl group, this is an electron releasing group. So here we have a resonance structure where there is an electron releasing group releasing electron density directly to a carbocation. So this resonance contributor is especially stable. Down here we have another one where we have an electron releasing group releasing electron density directly to the carbocation. So this one will also be an especially stable resonance structure. We can also think about this based on the resonance hybrid. Looking at this hybrid, we have partial positive character at this position right next to an electron releasing group, which makes this an especially good carbocation intermediate. In addition, if we look at the para intermediate, we have partial positive character on this carbon, which is directly connected to an electron releasing group. And so this is also an especially stable carbocation intermediate. Finally, looking at meta, we have our partial plus, we have an electron releasing group, but this group does not release electron density directly to a partial plus, so it's just not as good. Now let's think about this reaction in terms of an energy profile diagram. We first have the reaction with benzene, and I have the energy of the starting material and the energy of the intermediate. And keep in mind, we can think about the transition state leading to that, and this would be the activation energy. If we carry these over, let's pretend it's a nice straight line. If we set up toluene so that it's at the same starting point as benzene, these intermediates are going to be more stable than the intermediate that results from benzene because there is an electron releasing group that releases electron density to help stabilize the positive charge that's spread out throughout the ring. So all three of these have energies that are lower than the intermediate from benzene. Furthermore, that means that when we approximate the details of the transition state and the activation energy, it's going to look something like this. So now we can see that the transition state is going to be lower for all of these intermediates than it is for the transition state in benzene, which means the activation energy is going to be lower. And so this explains why toluene reacts faster than benzene. Because the intermediates are more stable than the intermediates resulting from benzene, and the transition state leading to those intermediates are more stable than the transition state leading to the benzene intermediate, then the activation energies are going to be smaller, which means the reaction is going to be faster. Another thing to consider, on the previous slide, we looked at how the ortho intermediate and the para intermediate are especially stabilized because there is the electron releasing group directly connected to a carbon that bears partial positive charge. These are going to be more stable than the meta intermediate, which means that the transition state leading to them are going to be more stable than the transition state leading to the meta product. So the reaction to give the ortho or para products will be faster than the reaction to give the meta product. So by considering the energy profile diagram of benzene compared to toluene, we have an explanation for why toluene reacts faster than benzene, and also why toluene gives primarily the ortho and para product rather than meta. Therefore, the methyl group, which is an electron releasing group, it is an activating group because it reacts faster, because it causes the reaction to happen faster, and it is an ortho-para director. So in general, electron releasing groups are activators and ortho-para directors. Next, let's look at the options for nitration of trifluoromethylbenzene. Just as we saw a couple slides ago, the nitro group can become connected ortho to the original substituent, and we can draw additional resonance structures, and these are going to lead to the ortho product. This can become connected meta to the original substituent, leading to the meta product, or it can become connected para, leading to these different resonance structures, and finally leading to the para substituent. If we look at the individual resonance structures, notice that right here we have the CF3 substituent directly connected to the carbocation carbon. Now, fluorine is much more electronegative than carbon, so the CF3 group overall is going to be a very electron withdrawing group. 3 fluorines are trying to pull electron density away from the carbon, so this carbon is going to try to pull away electron density from the group next to it. So it's trying to pull away electron density from a carbon that's already positive. So that means that we have a resonance structure that is especially unstable. Over here, we have the same situation where our electron withdrawing group is trying to pull electron density away from a carbocation, so this is also unstable. Now, because ortho and para have a resonance contributor that's especially unstable, what this means is that the overall carbocation intermediate is going to be less stable, so higher energy. In the case of meta attack, there's no especially bad resonance structure. So it's not that this is good, but it's not as bad as the ortho or para. Let's do the same thing with trifluoromethylbenzene, and we will compare the energy profile diagrams. So these are set up so that the starting point of benzene is at the same energy as the starting point of trifluoromethylbenzene. This represents the energy of the carbocation intermediate, and this represents the energy of the transition state leading to that. And so this would be the activation energy. Now, as we think about the carbocation intermediates for the trifluoromethyl substituted benzene, all of these are higher energy because we have an electron withdrawing group pulling away electron density from a ring that has a positive charge. So all 3 of them are going to be higher energy. If we consider the activation energy leading to each of these, so here we have the transition state, and then looking at the reaction progress, and then here is the activation energy. Here is the reaction progress, and so this is the activation energy. And here is the last one, and here is the activation energy. So because we have an electron withdrawing substituent pulling away electron density from a ring that's trying to share electrons with an electrophile, or we can think of it here, it's trying to pull away electron density from a ring that has a positive charge, all of these intermediates are going to be higher energy than the intermediate resulting from benzene. Therefore, they all have a higher activation energy than the activation energy for benzene, which means that the reaction will be slower than for benzene. And based on experimental evidence, we saw it was 40,000 times slower. Now, if we look more closely at the ortho, meta, and para, we see that ortho and para are especially destabilized because of the partial positive character right next to the electron withdrawing group. For the meta intermediate, it's not as bad, right? It's still higher energy, which means the reaction is going to be slower than what we have with benzene. But because this is lower energy and therefore the transition state leading to that intermediate will also be lower energy, it's not quite as bad for meta. So we can see that the reaction will be slower, but the reaction will be not as slow for meta. So when we have an electron withdrawing substituent, so an electron withdrawing group as our substituent. In general, these are deactivators, so the reaction is going to proceed more slowly, and they are meta-directors. It's not that the meta position is good, it's just that the meta position is less bad than ortho or para. So hopefully by working through the details of the mechanism and focusing on energy profile diagrams, I hope this gives you a good understanding of why there are activating and deactivating effects, and why some groups are orthopara directors while other groups are meta directors.